In this video, we're going to learn about acid and base strength, and we'll address the questions of what are the strong acids and bases, what makes an acid or a base strong, and how can we predict which side is favored in an acid-base equilibrium reaction. So firstly, the 7 strong acids you need to know are HCl, HBr, HI, HNO3, H2SO4, HClO3, and HClO4. Memorize them. Now, what is it that makes an acid strong? Well, an acid is strong if its conjugate base is stable. So if we look at HCl, its conjugate base is Cl minus, and that is a very stable conjugate base. Something that you can use to kind of anchor this idea is the fact that chlorine is very electronegative. So if you give it an extra electron, it's going to hold that negative charge quite well and be quite stable. H2S, by contrast, is a weak acid. It's not on your list of 7 strong acids. And its conjugate base is HS minus, which has a negative charge on a sulfur. Sulfur is not very electronegative, and so it doesn't hold a negative charge very well, and that makes H2S something that isn't as likely to give up its H+, so it's a weaker acid. Electronegativity isn't everything here, but it's a good starting point. Next, we'll address what the strong bases are, and they are the group 1 and 2 metal hydroxides. So sodium hydroxide, potassium hydroxide, barium hydroxide, and so on are strong bases. And what makes a base strong is its conjugate acid being stable. So if I look at the conjugate acid of hydroxide, it's water. This is a very, very stable substance. It is not very acidic, water. By contrast, Cl minus, its conjugate acid is HCl, which is not stable. This very easily ionizes to form H plus and Cl minus, and so Cl minus is a very weak base because it has a strong conjugate acid. Now, in an acid-base reaction, equilibrium will favor the side that has a weaker acid and base. So if we're looking to this first chemical reaction, we have HCl, which is a strong acid, and we have hydroxide, which is a strong base. If I don't specify it as potassium or lithium or whatever hydroxide, assume just hydroxide, it's going to be a strong base. On the other side, we have a weak conjugate acid and a weak conjugate base. So this is something that very heavily favors the right side. In fact, I would even say, forget the equilibrium arrows. This goes 100% to the right because we have the weaker side. It's a weaker acid and base by a significant margin. Next, we have the strong acid HCl and the weak base Cn minus at equilibrium with a weak acid HCN and a weak base Cn minus. Well, strong and weak give us weak and weak. The right side has weaker overall, so the right side will be favored with a little bit going backward. And next, we have a strong base hydroxide and a weak acid, giving us a weak acid and a weak base. Again, strong and weak giving us weak and weak. The right side is going to be favored because there's just less strength on the right side than on the left. Now, what if we have, though, a weak acid, HNO2, and a weak base, F minus, giving us a weak base of NO2 minus and a weak acid of HF? There still will be some side that's favored, but what we have to do is we have to look at this table right here. And basically, in this left side here, we have some acids. The higher up, the stronger the acid. And on the right side, we have the lower, the stronger the base. So I'm going to compare the acid HNO2 and the acid HF and just see which is the stronger acid. And I see that hydrofluoric acid right here has a Ka of 7.2 times 10 to the negative fourth, whereas nitrous acid has a Ka of only 4.5 times 10 to the negative fourth. So HF is stronger, and I'll say this is my stronger acid, even though it's not particularly strong. and I will say that we have a weaker acid in the HNO2. And that alone is going to be enough for me to tell that the left side is going to be favored. Um, because actually, if you wanted to, you could also look at the bases and you'd find that they correlate. So, for example, if we look at HF, its conjugate base is F minus, and notice that in relative terms, F minus, that base, is in the same position relative to the conjugate base of nitrous acid. The nitrite ion is a stronger base. Remember, lower on the base side is stronger. So we could actually say that this is a stronger base, and this is a weaker base, the F minus. So I didn't have to go there, but you can see you could either look at a comparison of the acids on each side or the bases on each side, and either way, you would get your answer. I do want to point out that if you multiply the Ka of one substance and the Kb of its conjugate base, always you're going to get the water constant of 1.0 times 10 to the negative 14th. Most obvious case being the hydronium ion up here with a Ka of 1.0 and the H2O, its conjugate base, having a Kb of 1.0 times 10 to the negative 14th. Multiply these together and you get the Kw. But you could also do the same thing for hydrofluoric acid with 7.2 times 10 to the negative 4th as the Ka, and F minus is Kb 1.4 times 10 to the negative 11th. Take this and multiply it by this, and you're also going to get the Kw of 10 to the negative 14th, any slight deviation being a result of sig figs and rounding errors. So I hope this video has helped. Feel free to leave any questions or comments in the comment section below. Thanks for watching.